Okay, guys, so I figured that since most of you are struggling with multiple choice, I just go on the internet, look for past papers, and then I attempt them. If I make any mistake, again, be vigilant enough to check and see if there's a mistake. I'll also, at the end, check the mark scheme, see if there's anything wrong. Then I can communicate that maybe, yeah, I can send just maybe below. I'll post this video on YouTube as a private video. And then I'll comment just below if I made any mistake or I'll edit the video, something like that. But anyway, let's try to go through this paper. And then I'm going to see what's in there, how I would approach the questions. Then hopefully it will benefit you. If you feel that it's beneficial for me to do this, I might spend my time and record a few videos to help you guys with your preparation. So this is the October-November 2023 paper, variant 13. I'm not going to, maybe I might spend over 1 hour 15 or less, I don't know, but because I'll be explaining, that might take a little bit longer, as opposed to if you're just writing the exam, you sit and write the exam. All right, so with this one, let's start. Question 1 says, I'm going to try to be fast. Sodium azide is an explosive used to inflate airbags in cars when they crash. It consists of positive sodium ions and negative azide ions. So when they say, so the formula is Na, N3. So if the sodium ion is positive, it's like this. It will balance with a negative here. So sodium is number 11 on the periodic table. That means after losing, because it's got a positive, it's got 10 electrons left. So I'll cancel C and D, they're out. So if I had to guess here, it's between A and B. So that's 50-50 if I have to guess. But now, I don't have to guess. If I think about the azide ion, it's got 3 nitrogens. So nitrogen is number 7. So if I say 7 times 3, 7 times 3, 21, plus the negative, 22. So that means A is out, answer is B. All right, we move on. Question 2, it says the graph shows the variation of the first ionization energy. So these are first ionization energies with proton number for some elements, okay? The letters do not represent the actual elements, okay? Which statement about the elements is correct? Okay. All right, so just if you are familiar with your syllabus, you know that this is kind of, because I gave 8 here, so 1, 2, 3, 4, 5, 6, 7, 8. So this is a period. So ionization energy increases across a period and decreases across groups. So these represent groups. These are elements of the same group. That's the end of the periodic table. Those are noble gases, I would guess. So you can see something like that. Yeah, but let's get into the options that they've provided us. So they say P and X are in the same period of the periodic table. P and X, no. P and X are in different groups, like I just said. So P and X are not in the same period. Period is going up. The general increase from Q to X, that's across a period, is due to increasing atomic radius. No. Ionization energy does not increase with increasing atomic radius. It would actually decrease if the radius was increasing, because the outer electron, the valence electron, would be further away from the nucleus. So this is wrong. The small decrease from, in fact, just to add on to B, what would be correct is that the increase is due to increasing nuclear charge, okay? Whereas shielding effect is remaining constant. So C, the small decrease from R to S is due to decreasing shielding effect. Where's R and S? Or this one, shielding effect? No, you cannot talk about shielding effect in the same period, because I've already mentioned that shielding effect remains constant in a period. So if this is a period, then we're not going to talk about shielding effect there, okay? Because these are first ionization energies. Unless maybe they were third ionization energies, then there can be a difference. Okay, the small, okay, now we're going to D. So this one already I've said it's wrong. So obviously I'm left with the D, because I know for sure that A, B, C are wrong, and I've given reasons. So I think the answer is D, but I have to check it. The small decrease from U to V is due to spin pair repulsion. Yes, that's true, because at that point, the S orbital is half, the P orbital is half full. So this is the P orbital. If let's say this was shell number 2 and shell number 3 and so forth, yeah, this can, you can see this is the D orbital here. You can see, so this one is period 4. This one is period 3, this one is period 2. So this will be 3s orbital, and this is 3p. Half of 3p is at U. So V, we start pairing. So the spin pair repulsion, answer is D. Okay, we move on. Aluminium carbide, which is that formula, reacts readily with aqueous sodium hydroxide. The two products of the reaction are sodium aluminum oxide and a hydrogen carbon, and a hydrocarbon, water molecules are also involved as reactants. What is the formula? The two products, okay? I see. React with sodium hydroxide. Okay, okay, this one I just have to write the equation. I'm gonna say aluminum 4C3 plus sodium hydroxide. They said water is also involved as a reactant, so I'll include it. And then I'll say that. So the two formula products are sodium, aluminum oxide, and a hydrocarbon, H. What am I writing? I want to write C first. So I say CXHY, because I don't know what the formula of the hydrocarbon is. But now let's see So the aluminium atoms are not balanced. So if I put a 4 here, that balances the aluminium, right? And then I need to put a 4 here to balance the sodium. And now if we have to balance our carbons, the carbons are 3, so maybe we might put a 3 here for now. And if I put a 3, they said it's a hydrocarbon. They didn't say what type of hydrocarbon. We don't know if it's an alkene. We don't know if it's an alkane. And what about our oxygens? So oxygen, so far we have how many oxygens? We have 4 plus 1 this side. So we cannot put 2 hydrogens this side. So obviously the hydrogens here, we have to put a bigger number somewhere. So we are going to affect our oxygens. So the oxygens so far, the oxygens this side, there are 4 times 2, 8. So I want 8 oxygens, but on this side I need to put a 4 here. So my oxygens are now 8, 8. And then the hydrogens are now 4 plus 8. 4 here plus 8 here. So that's 12. So I will need to put 12 here. But I cannot have a hydrocarbon that has 3 carbons and 12 hydrogens, right? I cannot have that. So I need to make sure. So I need to make sure I do something about this one. So that one will not work. But let's say I move this 3 and not put it in the formula, but put it up here. So if I put the 3 up there, then this divides by 4. So I divide here by 3. So divide by 3, then I get a 4. So my hydrogens will be 4 in the formula with 1 carbon. Do you understand? Because if I had 12 hydrogens, I want my hydrogens to be 12. But I removed the 3, I divided there. I said 3 over 3 to get a 1. So 3 goes up there. So 12 must also be divided by 3. I get a 4. So then I have 3 molecules of CH4. My equation will balance like that. It will balance like that. If I do that, I will have a balanced equation, right? 3 carbons, 3 carbons. And then here you have 12 hydrogens. What is 3 times 4? 12 hydrogens. Here you have 4 plus 4. That's 8. So we still need something to balance the equation. No, that's 4 here by 2, 8 by plus 4, that's 12. So the hydrogens are also balanced. So then my answer will be A. Again, just to explain again, I realized that this might be difficult to understand. What I did, just write the equation based on the information they gave you. They told you water is involved, include it. Then we balance the aluminium, we balance the sodium. Now, after you're done doing that, you will realize that you have 8 oxygens on the right, these 8 oxygens here, right? So we need to balance the oxygens on the other side. So then you need to include a 4 in front of the water. But when you put a 4 in front of the water, then your hydrogens becomes 8 plus 4. That's 12, right? And since you have 12 now, you cannot have C and 3 and H12. This one, there's no hydrocarbon that is this formula. Because our hydrocarbons, remember, it's alkene, which is CnH2n, and alkane, which is CnH2n plus 2. So this formula will not work. So I'm going to try now. So hence I said, what if I take this 3 and put it at the front? Then I have C3H, but I still want my hydrogens to be 12. But I want them to be 12, and this 1 carbon having 4 hydrogens around it. So that, because 1 carbon cannot have a double bond. So like this, and then it balances. So answer is A. Okay, moving on. A sample of 35.6 grams of hydrated sodium carbonate. Sorry, I can't see properly. Hydrated sodium carbonate contains 25.84 of sodium ions by mass. Okay, so this is hydrated. Okay, I like to write things. So this one will say we have sodium carbonate. So sodium carbonate dot XH2O. All right. Sodium ions are this. Okay, so you have this here, and this is the mass of sodium in there. So I have a calculator here. Okay, let me just use my phone as a calculator here. Where is my phone calculator? Okay, if I need scientific calculator, I don't have it on my phone. But anyways, that's 35.6 multiplied by 0.2584. So in this, in 35.6 grams, right, 9.19904 is going to be sodium. That's what they said, right? So which mass of water is given off? Okay, so we want to know how much water. So we can calculate that, because if this was sodium, we can calculate how much carbonate ion. What was the mass of carbonate in the 35.6? The way to calculate that is to say, am I right? Yes, I'm right. Yeah, that makes sense. So I could say, when I have sodium is 23, right? So when I have 46 grams of sodium, how much carbonate do I have? right? How much carbonate do I have? So I can say when I have 46, which is 2 times sodium, what is carbonate? Carbonate is going to be 12 plus 16 by 3. That gives me 60. So this will be 60 grams. But this time I don't have 46. I have 9.199 of sodium. So X here. So to solve for X is going to be 9.19904 that I had. Is that what I had? Yeah. And then divide that divided by 46 equal to, multiply that by 60 equal to 11. So this one will be 11.9987 grams. So these are the grams of carbonate, you see? So if I add these two and then subtract from 35.6, whatever remains is the water that was lost. So I'm going to say 11.99987 plus 9.199. Then I get total carbonate here, sodium carbonate, anhydrous sodium carbonate, would have been 21.1977 grams. Then from this, we subtract this one from 35.6. That gives me 14.4. 14.4. So when you subtract this, what is that? This mass here, this mass of the sodium carbonate, you subtract this one from the total mass of the hydrated salt, then you get 14.4. So that is the mass of the water. So that's the mass of the water that is kept. So my answer is C. I hope you understand that. So I'm just using ratios here. So again, what is 25.84%? That's what the question you asked me. What is 25.84% of this mass? And that will be sodium. So we found that, and then we said, what if I had one more of this one? This one, when you have 46 grams of sodium, you will have 60 here. So now the mass you got when you said 25% of that, you place it here. Okay, then you say X here. Simple. And then once you know the total mass of sodium and carbonate that is in the 35.6, you subtract that from 35.6, whatever remains, which is 14.4, was the water that was decomposed. If the term, again, this is when you completely decompose this hydrated salt. Easy, right? They say solid aluminum chloride. I don't know if you say aluminum. I say aluminium. Aluminium chloride sublimes. It sublimes at 178 degrees C. That's relatively low. Which it's actually low, relatively low, because it's not in the thousands, it's not even close to 1,000. Which structure best represents the pieces? So aluminium chloride, we know it dimerizes. You are familiar with this one. We always ask you to draw it. We say put aluminium here, and then another aluminium there, and then you do this, and then you are going to have chlorine there, chlorine there, chlorine there. This is aluminium trichloride. I'm drawing something that they've already drawn. So you put this one there, this one there. That's it. That is the aluminium trichloride dimer. You need to learn to draw the dot and cross as well. Right, so in a sample, because they are covalent compounds, so you are going to have the dimer. So where do they have the dimers? Okay, let's use process of elimination. It's not a salt, so this one is wrong. Again, it will dimerize. So this one we can leave it. It's aluminum trichloride. C, I'm not sure. Let's leave it. B, it's not the aluminum that donates the pair of electrons during the dative bond formation. So this direction is wrong here. So this one is wrong. Okay. So number one, we are left with A and C. If we have to guess between A and C. So because it dimerizes, you're going to have a dimer, okay? So Al2Cl6, and then another Al2Cl6. So when you want to vaporize this, you are breaking the van der Waals force that exists here, because it's going to have a van der Waals force in between, or you can say there's a London dispersion force. Okay, there's a London dispersion force, and then that's what you are breaking, because it's a physical change, not a chemical change. So you're not hydrolyzing, you're not breaking covalent bonds. So if I'm not breaking covalent bonds, then my aluminum trichloride dimer remains intact, just that I separate the molecules. So answer is A, because this one, there was hydrolysis. The dative covalent bond was broken. Nah, that's not what we're doing. Okay, so we leave that one. Answer A. Which row is correct? Okay, here we have shape of this is hydronium ion or acidified water, if you will, because I have a water molecule like this. Water molecule has two lone pairs of electrons. Here you can see there's a positive charge. That means a proton came in without an electron, and then there was a dative bond like that. So this now looks kind of like ammonia if you look at it. I have a lone pair that's free, and then I have 3 hydrogen bonds. I have 3 covalent bonds, sorry. This one to a positive. So this is a pyramidal. So this one is out, this one is out. Now we go to sulfur dichloride. So sulfur dichloride, Sulfur is in what group of the periodic table? Let's see my periodic table on the wall there. Sulfur is just below oxygen. So sulfur is in the same group as oxygen. So that means sulfur will also have 2 lone pairs here, and then a bond to chlorine and a bond to chlorine. Again, when you think about the valence shell electron pair repulsion theory, you know that lone pair repulsion here is greater than lone pair bond pair repulsion here. That squeezes this bond. Okay, so instead of having 109.5, you squeeze it. If I had 1 lone pair, I would squeeze it to 107. But because I have 2 lone pairs, I even squeeze it more. It gets even shallower. Then I have an angle which is more acute. It's 104.5. So this is a V-bent structure or nonlinear. Answer is A. This one is out. It cannot be straight when I have 2 lone pairs there, right? It's like water. Okay, good. Question 7. When an evacuated tube of volume, this is the volume, is filled with a gas at this. Okay, I see where this is going. This is temperature in kelvins, pressure in kilopascals, and the mass is this. Assume the gas behaves ideally, so that means I can use the ideal gas equation. What is the identity of the gas? So I will say PV. If when they say identity, I need the molecular mass. So I'm saying mass, and they've given me mass here over molecular mass. That's N RT, right? So the molecular mass is going to be equal to MRT over PV. And I need to use the correct units. So 0.65 times the gas constant, 8.31, times the temperature in kelvins, which is 300. And this divided by the volume. Okay, so the volume is 400. If you forget how to go from cubic centimeters to cubic meters, because your volume must be in cubic meters, quickly draw something like this, right? A cube. Okay, the volume of this, let's say this is a 1 unit thing. Let's say this is 1 centimeter by 1 centimeter by 1 centimeter. So this is a cubic centimeter, 1 cubic centimeter. But a centimeter, how many centimeters are in 1 meter? They are 100. So that means 1 centimeter is 0.01 meters, 0.01 meters, 0.01 meters, right? So that means the volume is going to be 0.01 times 0.01 times 0.01. So 1 cm cube is 10 to the minus 6 cubic meters. So multiply this by 10 to the minus 6. So you're going to have 400 times 10 to the minus 6. And then you're going to say times the pressure. That pressure must be in pascals, not kilopascals. So say 101 times 10 to the 3. You see, like that, easy. So I can see this 10 to the 3 will cancel this one and make it 10 to the minus 3. Right. Okay, you need to plug that in my calculator, but this calculator, again, not scientific. If I make it landscape, what happens? Okay, doesn't help. All right, I'm going to have to do with what I have here. 0.65 times 8.31 times 300. That's that, and then I put that in square brackets, and I put in brackets, and then I want to say divide by 400 times 10 to the minus 3 is what? Is 0.4, isn't it? Yeah, 0.4. 0.4 times 101. And I'm getting 40.1. 40.1, that's the MR. So the MR is 40.110 something I'm getting. So if I go down to the end of this paper, the periodic table, which gas has a mass of 40? It's argon, 39.9. So it's argon. The answer is argon. So we go back, we look for argon. Which question are we doing? Answer is A then, argon. That's the one with the molecular mass of 40.11, which is what you get there when you put that in your calculator. Okay. Right, nitrogen and carbon monoxide both have this molecular mass. Okay, so they have the same molecular mass. The boiling point of nitrogen is 77 kelvins. The boiling point of carbon monoxide is 82 kelvins. So they have slightly different boiling points. The intermolecular forces operating between carbon monoxide molecules are stronger. The boiling point is higher. Right? Boiling point is a physical change. It's got to do with the intermolecular forces. Right? What could be responsible for this difference in boiling points? Carbon monoxide molecules have a permanent dipole. The nitrogen molecules are not polar. Right? Looks like it. Let's pack that one. Looks like it was carbon monoxide. If you look at it, it's like this, right? And then oxygen donates here. It's like this, difference in electronegativity. Nitrogen is like this, same both sides. So A seems correct, but I'll pack that. Let's check the other ones. Nitrogen is sigma and pi bonding. What does pi bonding and sigma bonding have to do with the physical change? They are intra bonds, not inter. So they are not in between the molecules. So they don't count. So we don't even talk about this. Nitrogen is a strong. No, we're not breaking that. We're not breaking in bonds within. We are breaking between. The carbon monoxide molecule has more electrons than the nitrogen molecule. Nitrogen has 7 times 2, because it's 7 and 7. That's 14. Carbon monoxide has 6 plus 8, 14. No, they don't have different electrons. They have the same electrons. So A was correct, as we said. Good. And the electrons don't look, okay. Electrons matter when it comes to intermolecular forces. Why? Because when I talk about the van der Waals force, the strength of the van der Waals force is directly proportional to number of electrons. So you might want to consider D, but in this case, we see that they have the same number of electrons. Which statement about enthalpy change is correct? Enthalpy change. Enthalpy changes of reaction are always negative. No. Reaction? No, they can be positive or negative. This one is definitely wrong. Okay. Some reactions overall require heat, others overall release heat. Photosynthesis releases heat, isn't it? Oh no, photosynthesis requires heat. I want to say photosynthesis requires heat, but respiration releases heat. So reactions can be exothermic or endothermic. Enthalpy changes of combustion are always positive. Combustion, no, they're not always positive. When you burn something, you release energy, so delta H is negative. So definitely wrong here. It's supposed to be negative. Enthalpy changes of formation are always positive. Formation, no. When you form something, no. Because when you form, bonds are being formed. When you form bonds, energy is released sometimes. So no, most times. If you remember in IG1, we say when you're calculating delta H from bond energies, the right side, there's bond formation, which is exothermic, so which is negative. So I can bet now that C is wrong. So D, let's look at D. Enthalpy changes of neutralization are always negative. Neutralization. Yeah, this one is the correct answer, I would say. Why? Because when you are neutralizing, you are forming chemical bonds, right? You are taking the water molecules, and then you form a chemical bond, the salt and the water. So this one will be negative. Is there one that's correct here? Let me verify. Enthalpy changes of reaction are always negative. Incorrect. Enthalpy changes of combustion are always positive. Incorrect. Enthalpy changes of formation are always positive. Incorrect. Okay, so answer D. 10. What is the definition of standard enthalpy change of neutralization? Delta H standard neut. What is the definition? Okay, this is standard. Neutralization. Delta H standard when 1 mole of an aqueous acid is neutralized by an aqueous alkali. 1 mole of an aqueous acid is neutralized by an aqueous alkali. No, that's not true. It's not about 1 mole. This one is the one, it's this. This is a neutralization reaction. All neutralization reactions kind of summarize to this one. Acid plus alkali to form water. So you look for where they talk about water. So when 1 mole of an aqueous alkali is neutralized by an aqueous acid, that's not the case. It's not even always going to be like that. It's not about the 1 mole. And then when 1 mole of, it's not 1 mole of alkali acid. When 1 mole of an aqueous acid is neutralized by 1 mole, they can neutralize the different stoichiometry. When an aqueous acid, yeah, what I'm saying is, if you had a monoprotic acid like hydrochloric acid, it's different when you react to sodium hydroxide from when you react to diprotic acid like sulfuric acid. The stoichiometry is different. So you can't say 1:1 like that. Delta HR when aqueous acid and an aqueous alkali react to produce 1 mole of water. This is the one we said. We have to produce water, 1 mole. All right, this one, what is it called? This one, chloric or chlorate acid? Is it chloric acid? I will say chloric acid. Is the molecule that kills, it is the molecule that kills bacteria when chlorine is added to water. The following reaction produces this molecule. Okay, there it is being produced. Which statement about this reaction is correct? Chlorine is oxidized and reduced at the same time. Let's see, chlorine is an oxidation state of 0 here. In here, it will have an oxidation state of, let me work it out. Hydrogen is 1, -2 for oxygen, plus X for the chlorine equal to 0. So this one gives me what? X equal to +1. So here it's +1, isn't it? You don't even have to calculate like that. You remember, oxygen is 2 negatives. So one of the negatives is cancelled by hydrogen. So chlorine must be +1. And here chlorine is -1. So indeed, chlorine is being reduced and oxidized at the same time. It's reduced here, reduction, oxidation. Okay, so chlorine is both oxidized and reduced. That is correct. We can check the other ones. Chlorine is oxidized but not reduced. No, not true. We saw it. Hydrogen is both oxidized and reduced. Hydrogen, no, that's not the case. Here it's +1, there it's +1, there it's +1. Nothing like that is happening. Hydrogen is oxidized but not reduced. Again, not true. We move on with our lives. Right, nitrogen dioxide. Nitrogen dioxide exists in equilibrium with the dinitrogen tetroxide. Okay, the enthalpy of this reaction is -57 kilojoules per mole. Which conditions give the greatest percentage of this? So it's an exothermic reaction. In terms of temperature, okay, I was wondering what that cross is. Right, in terms of temperature, it's an exothermic reaction. So for an exothermic reaction forward, if you want to favor the forward reaction, which is exothermic, you must reduce the temperature so that the system will try to produce energy. In other words, to reverse what you have done. So we need a higher temperature. So that, we need a lower temperature. I said we need to reduce the temperature. We need to reduce the temperature. The system will favor the reaction, the forward reaction that is producing more energy, okay, more heat. So we need low temperature. So this one is out. this one is out. Answer is between B and D. So in terms of pressure, if we want to favor the forward reaction is 1 molecule of gas, this one is 2. We must operate at a higher pressure so that the system tries to reduce the number of molecules of gas. That's Le Chatelier's principle. So we want to, is that Le or Le Chatelier, it doesn't matter. We want to reduce the number of molecules of gas at a higher pressure. So I'm going to operate at a higher pressure. Between B and D, I want higher pressure. So answer is B. You see? But either way, if you had figured temperature or you figure pressure, then you can eliminate 2 and then you get 50-50. When an equimolar mixture of hydrogen and iodine react, the mole fraction of hydrogen iodide in the final mixture is X. What? All right. Hydrogen plus iodine are reacting. Equilibrium produces hydrogen iodide. So this must be 2. We are reacting equimolar amounts. So let's say this one 1, this one 1. So rice. Okay, rice. Let's say this one 1, this one 1. Initially 0 here. And then we are going to subtract. They say what? They say the final mixture is X. The mole fraction of HI in the final mixture is X. The mole fraction is X. You understand? So amount of HI, the number of moles of HI over the total number of moles is X. I could work that out by simply saying, let's say that at the end, this one is X. That means here I would have produced the X. That means here I would have lost half X. You see? That means here I would have lost half X. So now to solve the problem of having halves, I'm going to multiply this row by 2 so that I remove the half, right? So to remove the half, that means this one becomes minus X, but this one becomes 2X, right? So this one is going to be minus X because it's 1:1 ratio. This one is going to be 2X, right? And then down here, I have 2X. Okay, let's see, 2X at equilibrium. This one is going to be 1 minus X. This one is going to be 1 minus X. That's what remains at equilibrium. So Kp is equal to partial pressure due to hydrogen iodide, all this squared, divided by partial pressure due to hydrogen, multiplied by partial pressure due to iodine. So this is going to be 2X all squared over, this and this are the same thing. So it's 1 minus X all squared, right? Do we have an answer like that? Okay, the top part becomes 4X squared, the bottom part. So answer is C. Because the top part is 4X squared. The bottom part is 1 minus X squared. Answer is C. Right. In reaction 1, a student measures the initial rate of production of carbon dioxide when copper carbonate is added to that amount. So V here is given, concentration is given, number of moles can be calculated of the acid. Okay, in reaction 1, a student did that. So then in reaction 2, the student repeats the experiment using 50 cubic centimeters of. Okay, so the amount of acid here, the volume is still the same. The concentration here has been increased. We went from 0.1 to 0.5. So we increased the concentration of nitric acid and the same mass of copper carbonate was used. Okay. In reaction 1 and 2, the acid is in excess. So the acid is in excess. Okay. And samples of the same copper. Okay. So there's no issue here about using granules of copper carbonate or using fine powder or whatever. The particles have the same size, no issues with surface area here. So it says which row is correct? Rate of reaction 1. Reaction 1 is the one that was done with the lower concentration over reaction 2. So we expect the rate of reaction to increase. So we're going to have a smaller number divided by a bigger number, right? So that means because I increased the concentration in reaction 2 so much, then I expect the rate of reaction to increase so much. So it's going to increase. So we're going to have a bigger denominator and a smaller numerator. So this is a fraction, it's decimal. So this one is out, this one is out. We are left with C and D, less than 1. Then we go, they say, I gave 1/4 as an example. Please don't be confused. I'm just saying, if let's say the rate of reaction 1 is 1, the rate of reaction 2 is maybe increased to 4, then you are going to get a decimal. That's all I'm saying. This is just an example, okay? And then let's see, initial number of effective collisions in reaction 1 per second divided by initial number of effective collisions in reaction 2 per second. Obviously, when you increase the number of particles, that reactant particles in experiment 2, so you're going to have more collisions in reaction 2 than in reaction 1. So again, smaller number divided by a bigger number. So between these, we expect again this one to give a decimal. So answer is D. Okay, the forward reaction of a reversible reaction is exothermic and has an activation energy of 30. So the forward reaction is exothermic. Okay, so reactant molecules, you need to give them 30. Exothermic means I must go down, isn't it? Okay, let me just drop this one down a little bit. So I must go to products like this. So here's my profile, okay, guys. Okay, so here I need to supply 30 kilojoules of energy. So, okay, 30 kilojoules, that's my activation energy. And my delta H will be from there going down. So from here going here. They didn't ask, we just know. We have to think about it. So they say the reverse reaction proceeds by a mechanism that is exact reverse of the mechanism of the forward reaction. So we have to follow. If we are going back, it's a reversible reaction. Since it's exact, that means the mechanism will go back straight along the same path, going back here. So it's the same path. So they're saying you don't have to change this curve. You follow the same curve going back. That's what they're saying. Which statement about the activation energy of the reverse reaction is correct? The activation of energy of the reverse reaction is from here, going up here. That's the activation energy. You need to supply, because now our products are like the reactants now. We need to supply them with that much energy before they can react. So that's going to be 30 plus whatever. So the activation energy of the green, which is the reverse reaction, is going to be 30 plus delta H. Because remember, we had said this is delta H. Okay, so it's going to be 30 plus delta H of the forward. So what are they saying? The activation energy of the reverse reaction is equal to minus 30. No, it's not. Minus 30 is too small. It's up there. And regardless, it's not going to be exothermic. Activation energy is never exothermic. It's never negative. It's never negative. Okay, you don't reverse like that. It's never negative. Wrong. The activation energy for the reverse reaction is greater than 0 kilojoules per mole, but less than 30. No, it's greater than 30. You need more energy to go back. The hump is bigger from the reverse side. The activation energy for the reverse reaction is equal to 30. No, it's not the same as the forward reaction. Answer is D. The activation energy for the reverse reaction is greater than, yes, it's 30 plus delta H. Oh, sorry, my door. Someone, I heard a sound. I think it's my son there. Okay, question 16. X, Y, and Z are elements all found within groups 13, 14, and 15. Group 13, 14, and 15. On the periodic table, group 13, 14, and 15, that's boron, carbon, nitrogen. Okay, it's led by boron, carbon, and nitrogen. That's 13, 14, and 15. And then they say what? They say X is in the same group in the periodic table as Y. So X and Y are in the same group. Okay, so 13, 14, 15. X and Y are in the same group. But Y and Z are in period 3. So that's period 3. All right. Period 3 is below. It's right down here. It's aluminum, silicon, phosphorus. So Al, silicon, and phosphorus. So this is the situation. That's period 3. Aluminum, silicon, phosphorus. And then the first ionization energy of X is greater. Remember, X is the same as Y, same group. But the first ionization energy of X is greater than the first ionization energy of Y. So, okay, they are in the same group. That means X is above Y in the same group. You understand? Why are we saying that? Because as you go down, you are increasing shielding effect. So it becomes easier. So ionization energy must get less. But here they say X has greater ionization energy, which means it's smaller, it's above. So X is in period 3, I would say. So X is in this period. So X must be here. Y and Z are in the same period. So Y and Z are here. So this is the situation. So that's what we know now. X is above. And what did I write? Y and Z are down here. Whatever you call it. If you say Y and Z, that's up to you again. Okay. Right. Where was I? The melting point of Z is less than the melting point of Y. Y and Z are in the same period. So what are the trends in melting point across a period? Period 3. I know this one when I start from the beginning. I can say sodium, magnesium, aluminium, silicon. So, okay, so this one is sodium, magnesium, aluminium, silicon. What comes after silicon? Phosphorus, which must be way down because it's a nanometer. Phosphorus, and then sulfur. Sulfur is slightly up. It's here, but we don't need it because we can see it's not part of this equation here. Okay, it's not part of our problem. Right, so we are interested mostly, we want to compare what? Y and Z. So Y and Z are in the bottom period. So it's either phosphorus, silicon, and aluminium, right? Then they say the melting point of Z is less than the melting point of Y. So Z is less than Y. Interesting. Z less than Y. Okay, so if this is Z, that won't work because Z has to be less than Y, right? So we could say, okay, let me draw this back again. Z is less than Y. So if maybe this one is Z, this one is Y, or this one is Y, because they don't have to be next to each other. So Y can be this one or that one. Okay, so we don't know. So we could say that. Okay, we could say that. And then let's read more information. Y and Z both form chlorides, which are white solids. White solids. Okay, these they said Y and Z both form chlorides, which are white solids. These white solids react with water to produce solutions that are acidic. This is important. Chemical property. This is inorganic chemistry. All right. So this one, silicon tetrachloride, can react with water, right? Yes. Because they said form chlorides. It can. But does it form white solid, react with that? Okay, we'll pack that. Phosphorus chloride can be hydrolyzed. You form hydrochloric acid. This one you form hydrochloric acid. Aluminium, I see. Aluminium chloride reacts with water to produce an acid. Okay, the solution will be acidic. So if I say Y is this one, then Z has the melting point of Z is less than the melting point of Y. So this will then therefore not be equal to Z. So Z will have to be P because it must have a lower melting point. So P will be Z. And also this one forms hydrochloric acid when it reacts with water, isn't it? We are saying when we have PCl5, for instance, you can form, when you react, you can form an acidic product. The pH will be less than 4, very acidic, HCl. So I would say aluminium is my Y, phosphorus is my Z. Therefore, if Y and X are in the same group, then that means X is here. You see, because they must be in the same group. Then X becomes boron, Y becomes aluminium. So answer is A. Okay. All right, this one, you need to do a lot more work. You can see, just figure out all these permutations. So they combined physical properties and chemical properties. So the chemical property at the bottom was also important for you to make that decision. Which row about silicon and magnesium and their ions is correct? Okay, silicon, magnesium, and the ions of these guys. All right, comparison of silicon and magnesium. Silicon has a greater atomic radius. So, okay, I'll check things here. They are comparing atomic radius, electrical conductivity, melting point, and right. So let's look. They say silicon has a greater atomic radius than magnesium. No, atomic radius decreases across a period. So this one is not true, right? Silicon has a lower electrical conductivity than magnesium. That's correct. Yeah. Silicon yeah, doesn't conduct electricity like magnesium. Magnesium is a metal. Silicon, no. All right. C, silicon has a lower melting point than magnesium. No, it's a giant covalent structure. It's got a higher melting point. So if you have to guess between B and D, 50-50 here. But don't just jump to guessing. Let's check. The radius of silicon 4 ion is smaller than the radius of magnesium. Yeah, that's true. Ionic radius also decreases because of increasing nuclear charge. Okay, but for ions, remember it breaks. It's like this, and then it starts up again. So be careful. So yes, it decreases. So D, in terms of magnesium and silicon, is correct. Let's find now the explanations. Silicon has 4 delocalized electrons per atom. They said silicon has lower electrical conductivity. So if silicon has lower electrical conductivity than magnesium, and then the explanation is that silicon has 4 delocalized electrons per atom, magnesium only has 2. This is a contradictory statement, because if silicon has lower electrical conductivity, then we cannot argue that it has lower electrical conductivity because it delocalizes more electrons. That doesn't make sense. Because if it's releasing more charge carriers, then we expect it to have higher electrical conductivity. But we have said here it's got lower electrical conductivity. Then we cannot argue that it releases more charge carriers. This one I'm suspecting B is wrong. Let's check the explanation for D. Silicon has a greater nuclear charge than magnesium. True. Ionic radius and atomic radius in the same period will decrease because of nuclear charge. Answer is D. Again, we knew because B was contradicting in terms of those charge carriers there. Bromocresol, is it bromocresol? Or yeah, I think so. You can call it that. Bromocresol green is an acid-base indicator. Okay, this is an indicator. Okay, below a pH of 8.3, it is yellow. Above that is that. Okay, this one is where I do this. I say, what are the pHs? They say 3.8. This is my scale of pHs. And then here I have a pH of 5.4. And then they say below a pH of, where is yellow? Okay, I'll put, what colors do I have? Yellow. So here it's yellow. Between these, it's green. Okay, here it's green. Above, it's what color they say? blue. Okay, above is blue. Where's my blue? Okay, let's just get that. This blue. This one is blue. So it's like this. So this is the situation. Okay. This is the situation. So now let's read. Bromocresol green is added to the aqueous solution formed when the chloride of T, element T. So there's an element T. We don't know what it is. When that element T is added to water, the color becomes yellow. Okay, so this element T reacts with water to form an acidic solution. That's why it becomes yellow, because the pH drops. Remember the vertical, this is pH. So the pH drops. So compound T must form an acidic product. Usually it's HCl, usually it's whatever. We will see. So compound T, here they didn't say, they say, oh yes, they said when a chloride of compound T. So when it reacts with water, does magnesium chloride react with water? No, it doesn't. It's like sodium chloride, it dissolves. C and D are out. Answer is between A and B, because silicon tetrachloride reacts with water. We said that before, right? So that argument we got. We need more information to decide now between A and B in terms of element U. When in excess of the element of the solid oxide of element U, so we have solid oxide of U, is slowly added to this yellow solution. So it's going to react with the HCl. That's what I can tell you, because the yellow solution is acidic. Okay, so whatever we are adding is a base. It's going to react with we slowly add it to this acidic solution, and then the indicator starts turning blue. So we go back to alkaline. So it's going to form an alkaline solution after reacting with this. So what does it mean? What does it mean? It's like you have an oxide of U. So U oxide plus, let's say, HCl, kind of neutralization reaction. So it neutralizes. It goes through green and then it neutralizes. But at some point, you are now going to have more of this oxide. At some point, as you keep adding, because they said you slowly add the oxide. At some point, you go above the neutralization point, and then you are in the alkaline region. The indicator turns blue. So which one is it? Is it phosphorus oxide or is it sodium oxide? I would guess that it's sodium oxide, because it's going to form sodium hydroxide when it reacts with that. You see? Sodium, this one, when it starts reacting with the water, because initially when it reacts with this, you are going to form sodium chloride in water. But above that, above the neutralization point, when all the HCl is gone, you start forming a hydroxide. Because if we had phosphorus oxide and we react with this, and then we react with water, the solution would remain acidic, because phosphorus oxide would form phosphoric acid. So the pH would remain low and the solution would remain yellow. You see? So my answer would therefore be A, because this one will remain acidic. Okay? Which row correctly describes the separate reactions of calcium and strontium with water? Calcium and strontium are in the same group. Remember I told you guys, think about sodium, magnesium, and what's below sodium? Potassium. Potassium is more reactive. So reactivity increases this way. Reactivity decreases this way. You see, so it increases that way. So magnesium is less reactive than sodium. But sodium is less reactive than potassium. So this is the direction of reactivity, these arrows. This way and down, like so. So if calcium is here, that means calcium is more reactive than magnesium, because it's down the group. So calcium is more reactive than magnesium. So we know that. So we're just going to keep that at the back of our mind. So substance, when we react with the water, so calcium is going to react. Which one are we comparing? We're not comparing magnesium. We're comparing calcium and strontium. Strontium is below calcium. So calcium is more reactive. So I'm going to say more reactive. Strontium is more reactive, yeah. Substance are reduced when we react with water. Okay, let's try that. Separate reactions, calcium and strontium with water. So calcium plus H2O to form calcium hydroxide, right? Calcium hydroxide plus what? I don't know. Hydrogen gas? Yes, to form hydrogen gas. Metal plus water. Right, so plus hydrogen gas. Remember, I said plus hydrogen gas here, but we don't care about that. What we care about is that water lost oxygen. The oxygen was given to calcium, and then the hydrogen was left alone. So water was reduced. So substance reduced is water. So this one is out, this one is out. The substance reduced is water, because water loses oxygen. So now we said substance oxidized. Obvious, these ones we can't distinguish, they gave the same thing. So we have to use the other point. Which one is more, gives a more vigorous reaction? The more reactive one is strontium. So answer is D. L and M are both compounds of group 2 elements. L and M are both soluble in water. L and M are compounds. They are not atoms of group 2 or elements of group 2. They are compounds. So say magnesium oxide, calcium oxide, whatever, nitrate, whatever it is. They are both soluble in water. Okay. When solutions of L and M are mixed, a white precipitate is formed. Okay. They must be both soluble in water. And when they are mixed, they must form a precipitate. Is barium chloride soluble in water? Yes, it's a chloride. Is magnesium sulfate chloride soluble in water? We said for group 2, solubility. When we talk about solubility for group 2, if you remember, we just do this. And then we say solubility for sulfates. And then we say solubility for hydroxides. For hydroxides, magnesium hydroxide is highly insoluble. So solubility increases as you go down. Solubility of sulfates decreases as you go down. So magnesium sulfate is soluble because it's up. It's a sulfate and it's up. Magnesium is up, so it's soluble. So in terms of solubility, both of these are soluble. When they mix, barium will react and combine with sulfate. Okay, this looks like the answer here. Because we test for sulfate using barium in paper 3, because it will precipitate and form a white precipitate of barium sulfate. So this one looks like the answer. Let's check the other ones. Barium sulfate. Barium sulfate is down here. It's insoluble. They said both of L and M must be soluble. This is insoluble. This is wrong. Barium nitrate, all nitrates are soluble, so we're good here. We're fine. And magnesium chloride is also soluble, so we're fine in terms of solubility. When we mix them, this becomes barium chloride, which is again still soluble. And magnesium nitrate, so no precipitate here, so this one doesn't work. Although they are both soluble, they cannot form a precipitate. Barium carbonate and magnesium nitrate, this one is going to form barium nitrate. All nitrates are soluble, so barium nitrate, no precipitate. Magnesium carbonate, no precipitate, so not this one. So answer is A, as we had suspected here, guys. What I did. Okay, a 5-gram sample of an anhydrous group 2 metal, nitrate loses 3.29 okay, group 2 when heated strongly. This is thermal decomposition of group 2 nitrates. They didn't say what it is, so I'm going to write metal. Let me write it like this, man. I'm going to say metal nitrate, like that. If it's group 2, then I need a 2 here. Decomposes to form metal oxide plus nitrogen dioxide, if you remember, plus oxygen. Right, to balance the equation, this is the equation that we balance with the 4, isn't it? Put a 4 here, and I put a 2 here, and a 2 there. 2 M's. M is not an element, it just represents any group 2 metal, right? And so I had 5 grams here, and these 2, because these are the gases, nitrate loses this. So this was the mass that was lost. These are nitrates. Let again get my phone as a calculator here. So the magnesium oxide was what? Magnesium oxide. No. Why am I saying magnesium? I wrote M. M represents any metal of group 2. So that's 5 minus 3.29. 3.29. That's 1.71. So here you had 1.71 grams here. So now, which metal is present? Right, which metal is present? Okay. We're good here. I could do that. Right. Notice that. Can I work it like that? Can I work it like that? I can. So I'm going to show you. I think let me show you what will be easy for you to do in the exam. But there is a method that I'm thinking it will solve this one. I will explain it. Let me just explain what you do. So if I know, because I would calculate that when I have 4 moles of nitrogen oxide plus oxygen here, what is the mass of nitrogen in here and what is the mass of oxygen? So I can calculate that. Okay. So what is the total mass here? What is the total mass here of 4 moles nitrogen and 1 mole oxygen? So you add the molecular masses here. Then you ask, of this, how much of it is oxygen? Okay. So we are saying if you had these moles, how much of it is oxygen? Then you say, but I don't have this mass. I have 3.2. So 3.29 would have how much oxygen? Question mark. So don't say O2, just say oxygen atoms. So how many grams of oxygen are in there? How many grams of oxygen are in there? And 3.29. You can work it out. If you know the total mass here, then you can do a ratio to say in this mass, total mass, oxygen is how many atoms are in there? 10. 10 times 16, 160. So 160 grams is oxygen in this total mass, right? So what about, so if you know the total mass you put here, you say that gives 160 grams here. So calculate the total mass is just as simple as calculating molecular masses. And then when you do that, then you know the oxygen. Then if we know this oxygen, we can calculate how much oxygen was here. You see? And that we can calculate. We have a way for doing that. Because if we know the nitrogen here, this nitrogen, we know it. All of it came from here. So we will know this mass of nitrogen goes with this mass of a certain mass of oxygen. So then we can calculate the mass here of oxygen that we had initially all together in this one. And then we use that as a ratio to find out how much mass of oxygen was in the original compound. Then when we take that, we compare with this one here. How much oxygen would then be here? Because some of the mass of the oxygen, we found it to be present in here. That's a long process. So I'm going to spare you that. If you want me to explain, you can comment. You can just let me know. Just let me know. I'll do it. I'll show you. It works out. You get the molecular mass of the metal if you do that. We use empirical formula at the end. But in the exam for a question like this, I'm going to test. I'm going to say magnesium carbonate, magnesium nitrate. Ratio with magnesium oxide is 1:1. So if I don't get the mass of 1.71, then I know it's not the metal. So I'm going to say, what is magnesium nitrate? Magnesium nitrate is what? Nitrate is, what is 16 times 3, 48, plus 14, that's 62, times 62, sorry, times 2, 124. So this guy here is 124, okay? Let's just keep that in mind. But we need to add the magnesium. So it's going to be this plus the 24 of magnesium. That's 148. So the total mass here is 148. So when you have 148 grams of magnesium nitrate, you will get magnesium is what? 24 plus 16. That's 40. So you will get 40 grams here, okay, of magnesium oxide. But this time you don't have 148 grams, you have 5 grams. So let's see, does this give us 1.71? So we say 5 divided by 148, we get 0.0333 times 40, we get 1.35. Nah, 1.35 is not 1.71, incorrect, so it's not magnesium. Then again, we can just change, if it was calcium, then I change this one to calcium, this one to calcium. So calcium oxide, calcium nitrate. Then the masses will change here, the mass will change here. Calcium nitrate is 40 plus 16, that's 56. No, calcium oxide is 56. Calcium nitrate is going to be 124 plus 40. 124 plus 40. Don't need a calculator for that. It's 164. Okay, I already used the calculator. Okay, so 5 divided by 164 equal to 0.030487 something. Multiply that answer by 56, 1.71. Okay, this one is the answer, 1.7073. This is 1.71 grams, which is this mass we had here. So answer is B. Done. Okay, so you can just test like this, but there's another way where you don't test, you just actually work it out. And I can show you that way if you tell me you want to know how to do it. In this question, it's just a longer way. In this question, Q represents an atom of chlorine, bromine, or iodine. Okay, chlorine, bromine, or iodine. That's Q. Which explanation for the variation in volatility down group 17 is correct? Group 17, we know that it goes from gases to solid, gases to liquid to solid, isn't it? We know that fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. So volatility is decreasing as we go down. The bonds are becoming stronger. So volatility is decreasing. If this is volatility, it's decreasing. Okay? Volatility means the easiness by which a substance has to evaporate. Just my phone. Let's see. So what does that mean? So that means the bonds are becoming stronger, right? Let's go down. Instantaneous dipole to induce the dipole forces between molecules become stronger. Yes, they become. We said it. So volatility decreases. A might be correct. Permanent dipole to permanent dipole forces between molecules become stronger. No, there are no permanent dipoles between halogens because they have the same electronegativity, the chlorine and the chlorine, the bromine and the bromine, the iodine and the iodine. So no permanent dipoles here. So B is nonsense. The bond energy of the Q2 molecules, decreases. Doesn't matter. Volatility is not about bonds within. So the bond energy, yes, it decreases because the atomic radius is getting bigger, shielding effect is getting bigger. But volatility has got nothing to do. It's a physical change. It's got nothing to do with the bonds within. So this one is wrong. The first ionization energy decreases. What does ionization have to do with evaporizing something? It's not to do with that. It's breaking intermolecular forces. Answer is A here. Which statement about the halogens or halide ions is correct? Okay, bromide ions react to form a white precipitate when added to silver nitrate. Okay, these are about displacement reactions of halogens. The reactivity of halogens, the ones at the top will displace the ones below. So fluorine displaces chlorine, chlorine displaces bromine and so forth. So if they say what bromide ions react to form a white precipitate when it's added to silver nitrate. No, This one is not correct. The bromine doesn't form a white precipitate. It forms a cream precipitate, not white precipitate. This one is wrong. Bromine does not oxidize chloride ions when added to sodium chloride. Okay, so in sodium chloride, the chloride is Cl minus. If bromine displaces it from there, it will become Cl2, which is charge 0. So yes, this is oxidation. Okay, yes, it is oxidation because it's an increase in oxidation state. But can bromine displace chlorine from sodium chloride and make it into chlorine? Remember in your book, you have this picture with halogens with test tubes, and then they put an organic solvent because halogens dissolve better in an organic solvent. So once the CO2 is formed, it will go into the solvent, the organic solvent. But can it be formed by using bromine? Can I use bromine to displace chloride? No, because I told you the one above displaces the one below. Bromine is below. So they say bromine does not oxidize. Yes, it does not oxidize. So this is true, actually. It does not oxidize. It cannot because chlorine is above. Fluorine atoms form cations by accepting electrons does not make a thing positive. It cannot become a cation by accepting electrons. This is wrong. Chlorine ions are stronger reducing agents than iodide ions. Okay, what is a reducing agent? A reducing agent is one that is itself oxidized. Oxidation is loss of electrons. So this statement is saying chlorine is better at losing electrons than iodide ions. No, chlorine is above, so it's smaller. So its electrons are close. It's more electronegative. Iodine is actually good at losing electrons. So we started from the definition of a reducing agent. A reducing agent gets oxidized itself, which means it loses electrons. For it to lose electrons, it means the electrons are too far from its nucleus, so that you can easily lose them. But that's not the case here. Chlorine's electrons are closer, so it's not going to be very good at losing electrons. This is wrong. Answer is B. If ammonium cyanate is heated in the absence of air, so there's no air, this is important, no oxygen being contributed from elsewhere, the only product of the reaction is urea. So this is urea here. No other products are formed. What is the formula of the cyanate? Ammonium cyanate. Ammonium cyanate. Okay. So if I look at the product formed, it's got carbon, oxygen, nitrogen, and hydrogen. I have nitrogen and hydrogen, so I need carbon and oxygen. So oxygen cyanate. Like so. So this is the cyanate ion. So this one is the cyanate ion. Isn't it? Because one ammonium, one cyanate. Do these atoms add up with those in urea? One carbon, one oxygen, one oxygen. 4 hydrogens in ammonia, 4 hydrogens in ammonium, 2 nitrogens, correct. So cyanate is this one, C. Okay, hexaamine is a crystalline solid used as a fuel in portable stoves. The diagram shows the skeletal structure of hexaamine. Why is it hexa? Hexa means 6. 1, 2, 3, 4, 5, 6 carbons. Okay, it's got 6 carbons. Okay, it's got 6 carbons. It's got 4 nitrogens and all. What is the empirical formula? Okay, empirical formula. We start with the molecular formula. It's got 6 carbons. It's got, I don't know how many hydrogens. It's got 4 nitrogens that we can see. Let's count the hydrogens. 2 here, 2 there, 2 there, 2 there, 2 there, 2 there. So that's 2 by 6, that's 12. So it's got 12. Let's simplify this. What is the thing to divide with? 2. C3, H6, N2. Do we have that? C3, H6, N2, B. Answer is B. Right, the compound aspartame, all right, is widely used as a sweetener in diet soft drinks. Aspartame is chiral. There are no chiral carbon atoms in C6H5. Where's C6H5? Oh, this one. They were lazy to draw this thing. This one. It's this one. That's C6H5. But anyway, it doesn't matter. They said there are no chirals there. All right, let's see. So they wonder us how many chiral atoms, carbons. You don't have a chiral carbon when there's a double bond. So this one is already out. This one is out. This one is out because they're double bonds. The methyl up here, this one they already told us is out. The methyl up here is 3 hydrogens around this carbon, so out. This one has 2 hydrogens on it, out. This one also has 2 hydrogens, out. So we have a chiral here, and we have a chiral carbon here. Okay, so 2 chiral carbon atoms. How many sigma and pi bonds in the molecule? That I can't make that up without drawing it, so I will draw it. Where should I draw it? Maybe let's draw it up here. So the CH, how can C be C to C and then H? That should be a triple bond. So C triple bond C bonded to a hydrogen. So the second carbon is bonded then to a third carbon, and that third carbon is bonded to 2 hydrogens. And then after that, we have another CH2. And after the second CH2, we have a CH. Okay, there's 1 hydrogen, and then we go to carbon. So there's a double bond there. And then there are 2 methyls. So this is C with the methyl and the methyl. Okay, methyl. Here's the methyl. And I'll draw the other methyl here. Okay, so these are all the bonds present. How many sigma, how many pi? Remember, when you have multiple bonds, only one is sigma. So 1 sigma, 2 sigma, 3, 4, 5, 6, 7, 8, 9, 10, 11. Remember, only one. 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 sigma bonds. Oh, there's only one answer with 19 sigma bonds. This one, D. That's the answer. The hydrocarbon 17H36 can be cracked. Okay, which compound is least likely to be produced in this reaction? Okay, right. Sorry. Oh, I realized I was leaning too forward to see. I can't see properly, so I'm leaning too forward. But anyways, catalytic cracking, we know you have a long chain hydrocarbon like this one, 17 carbons, 36 hydrogen. It's an alkane because 17 times 2 is 34 plus 2, 36. So it's an alkane. So this hydrocarbon is an alkane. When we crack it, it's going to form short chain alkanes and an alkene. So if we look at these, you will see that this one is unusual here. I don't know why they put they put it because that's the answer. Because if I remove one carbon from here and I get C16, and this is an alkane or alkane, 16 times 2, 32 plus 2, this one is an alkane. So the next thing must be an alkene. So, but I'm left with one carbon to get to 17. So I cannot form an alkene with one carbon. So this is unlikely to form because I need an alkane and an alkene. And yet I'm left with one carbon, and one carbon cannot form a double bond. So this is the answer. Okay. Which compound has an MR of 84 and will react with HBr to give a product with molecular mass of that? Okay, two things must be made. First, it must have this mass. Let's check which one is that mass. 1, 2, 3, 4, 5, 6. Okay, so it's an cyclic alkane, so it will have a formula of C6H12 because it's cyclic. So it will have, it's an alkane, an aliphatic compound, but it's going to have a formula same as the general formula of an alkene. You can count it's 2 hydrogens on each carbon. So if I say 6 times 12 for the carbons, 72, plus what? Plus 12. That's 84. So this one does have a mass of 84, so it qualifies. Let's look at the next one. 1, 2, 3, 4, 5, 6, 7. So 7 by 12, 7 times 12. Plus how many hydrogens? If you have, it's an alkene. So if you have 7 carbons, it means you have 14 hydrogens. So 7 times 12 is 84. If I add the hydrogens, the mass goes beyond 84. So this one doesn't have the correct mass. Okay, incorrect mass, this one is wrong. And then this one is 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. 5 by 12 is 60, isn't it? 60. Plus oxygen is 16, 76. 76 plus how many hydrogens? 3, 2, 2, 3. This is 10 plus 10. 76 plus 10 plus 10. 86. 86 is not 84. The mass here is also wrong. Let's check D. D is 1, 2, 3, 4, 5, 6. 6 by 12, again, 72 plus, if you have 6 carbons, you have 12 for an alkene. You have 12 hydrogens. So 72 plus 12, 84. The mass here is correct. Right, so answer is between A and D. Right, they say we will react with HBr. We know alkanes only undergo really combustion, which is oxidation, and free radical substitution. Those are the main reactions they undergo. So if I just add HBr, this is not going to react. The first one is not going to react. I don't even need to check this mass. You can check it yourself. But I know alkane is not going to react with HBr. But I can add, you see, I can do electrophilic addition reaction to this double bond. So answer is D here. Okay. Beta carotene is responsible for the orange colors in carrots. There it is. It is oxidized by what concentrated? These are harsh oxidizing conditions, breaking double bonds. Okay. So let's see. When an individual molecule of beta carotene is oxidized in this way, many product molecules are formed. How many of these product molecules contain a ketone functional group? All right. We are going to break here. We're going to break there. We're going to break there. We're going to break here. Everywhere I'm putting a line, you're going to break. You cut right the way I'm doing. Right. So let's see. Now, let's get my red pen. This side, when you break, right? Let me put it this way. When you break something like this, you put an oxygen. So this double bond stays and then you put the oxygen. Then you say double bond, then you put oxygen. Then whatever is connected. So that's all you do when you break. So this side here is going to have O, that's a ketone because of this methyl, so it's going to be a ketone. But this will then straighten up going all the way and to cut here, and then this side will be an aldehyde. But because of the acid oxidation conditions, this one is going to be a carboxylic acid side, COOH. So it's going to have a carboxylic acid terminal with a ketone here and a ketone here. So this side, this thing will make one thing that is got two ketone functional groups. And this one will be an aldehyde because of the hydrogen here, then becoming carboxylic acid. But this side, because of the methyl, this also forms a ketone functional group. You see it like that. This one, there's a hydrogen here. So this one is out. This one is going to be a ketone. This one is out. This one is out. This one is going to be a ketone. This one is out. This one is going to be a ketone. And obviously, this one is the same as the one we discussed before. It's going to be a ketone because of this methyl here. So I have 1, 2, 3, 4, 5, 6. Answer is B. Okay, 1.1 dichloropropane reacts with aqueous sodium hydroxide in a series of steps to give propanol. Okay. 1.2 dichloro. Okay, so 1, 2, these are 3 carbons, and then you have chlorine here, and then you have another chlorine there. So this is the compound 1.2 dichloro. Yeah, you can see that. And then we want to go in a series of steps. We want to get to this guy. Right, this is an aldehyde. Propanol. Right, propanol. Yeah. So they say we want to go there. I would do what? Okay, we have sodium hydroxide aqueous. Because it's aqueous, aqueous sodium hydroxide, and the halogen alkane. That's a substitute. Please provide a complete question. I need more information. Sorry, my phone. Then, where was I? Aqueous sodium hydroxide, if you remember this one in your book, when you're looking at carbonyl compounds, is it carbonyl compounds? I forgot, sorry. Halogen alkanes. Because this one is a halogen alkane. Chloro something is a halogen alkane. When you use aqueous sodium hydroxide, you get a substitution reaction. When you use ethanolic sodium hydroxide, you get an elimination reaction. You form a double bond. So here, I'm going to change this one to maybe, let's say I substitute it, and then maybe it's a double substitution. Can it be double? I don't know. Maybe 1. Yeah, maybe 1. I don't know. Let's say maybe we'll do this one. Right? Let's say we'll do this one. Right? Like that. We have done a substitution reaction as a first step. The next step, this is retrosynthesis. We're kind of working backwards, isn't it? No, is it retro? I don't know. This one. Just figure out the steps. Yeah, it's retro because we need to know how we came from here to the final product. So it's a retrosynthesis. So now we need to write. I have that chlorine. Can I remove hydrogen chloride from this using an elimination reaction? And then end up with something like this, OH, like so. And then add hydrogen here. I add hydrogen, hydrogenation in the presence of platinum or nickel. And then I remove the double bond. And then I get this alcohol. And then oxidize this with an oxidizing agent like potassium dichromate. And then I get my aldehyde. You see, I can do this series. They said a series of steps. The first, what term describes the first step of this reaction? It's substitution. I'll say substitution because you have to substitute the chlorine, put OH. I don't know if you substitute both chlorines, but I'll do this. So the first, after you have that, then you eliminate to form the double bond. After that, you remove the double bond by adding hydrogen using platinum or nickel catalyst. And then you have a primary alcohol. Primary alcohols can be oxidized to aldehydes. Isn't it? Right. Propanoic acid can be made from bromoethane using a 2-stage synthesis. So 2-stage synthesis. We are coming from what? Propanoic acid can be made from bromoethane. Bromoethane is this one. And we want to 2-stage process to form propanoic acid. Propanoic acid. All right. What do I see? I see F and I see prop. Interesting. 2 carbons, 3 carbons. How did it happen? Obviously, I had to add somewhere a carbon. So what you would have done is maybe we had to use hydrogen cyanide. Remember, to add carbons, there are a few ways. Normally, if you want to add 1 carbon, hydrogen cyanide, you use cyanide in potassium cyanide. Hydrogen cyanide and potassium cyanide. Or maybe just check to see if the number of hydrogens and everything else changed. Otherwise, it might have been an esterification reaction where a methyl, methanol was added to a carboxylic acid. But this is not the case. So I would say here, hydrogen cyanide was added, and then we got this guy. I have out. So this then becomes another carbon here. So cyanide, you see, triple bond N. And you know, to go from this to that, this is where the reaction in your book that if you have a nitrile compound, like this one, the one in the middle, this is propane nitrile. The propane nitrile can be converted to a carboxylic acid by using HCl, dilute HCl. So number 1, we need a source of cyanide. So this one is out. This one is out. Red pen. B and C are out because step one, we need cyanide. I said earlier on, potassium cyanide or hydrogen cyanide. So we need cyanide and we need dilute HCl. A has sodium hydroxide. A is out. Answer is D. Okay. Alcohol X gives a yellow precipitate with alkaline iodine. Alkaline iodine, the moment I see this, I write iodoform reaction or try iodomethane reaction. What is the structure of X? Iodoform is positive with methyl ketones. So let's look for a methyl ketone here. A, B, C, D. All of these are alcohols. So we don't have a methyl ketone. But we know that secondary alcohols, some secondary alcohols, the ones that have a methyl, can be oxidized to a ketone, which is a methyl ketone. And then that methyl ketone gives a positive test. So let's look for a secondary alcohol that is a methyl. So if I oxidize this one, I remove this one, and then I put a double bond. You see, this doesn't work because there's no methyl ketone here. Okay, remember, you cannot oxidize these guys further. So this one is out. This one is a primary alcohol. It doesn't work. You need a secondary alcohol. This one is a tertiary alcohol. So you cannot oxidize this to a ketone. It doesn't work because you cannot oxidize it. It's a tertiary ketone, a tertiary alcohol. So answer D. Yes, it makes sense because if I remove this, then I form a methyl ketone. This methyl and the ketone. And this will give you a positive iodoform test. Well done. D. I'm saying well done. All right. Anyways, when ethanol reacts with sodium metal, ethoxide ions are produced. When water reacts with sodium metal, OH ions are produced. Which statement about these reactions and the ethoxide ion is correct? At the same temperature, the same rate of reaction, the rate of reaction between sodium and ethanol is greater than the rate of reaction between sodium and water. Oh, no. No, the rate of reaction. Okay, we'll pack that, but I don't think so because we have the same temperature, we have the same everything, and it's a 1:1 reaction. So I don't think so. So we'll pack that. Let's look at the other options. Ethoxide is greater base than OH due to the electron donating effect of the ethyl group. Let's see. OH minus. We can test that. OH minus is like this. Okay, this is OH minus. Ethoxide is like this. CH2, CH3. Like this. This is an alkyl group. It's electron donating. It pushes negative charge here, making this one more negative, increasing the ability of this guy to accept a proton. So the electron density on the oxygen will increase because of the positive inductive effect of the alkyl group. So does that, which increases its ability to accept a proton, hence it becomes a beta base. So ethoxide is a stronger base than this. That's correct. It makes sense. But yeah, so I think answer is B. Let's check the other ones. The negative charge on the oxygen in an ethoxide ion is delocalized. Delocalized where when there's only one atom. It's not delocalized to where. It is easier to deprotonate ethanol as it is more acidic than water. So they're saying ethanol is more acidic than water, and it's easy to deprotonate it. It's easy to remove a proton from ethanol. Ethanol will be this guy. This is ethanol. Again, we said alkyl group donates negative charge, increases the negative charge here or negative electron density. This causes this one to attract more here. So it becomes difficult to remove the proton. So it's not easy to deprotonate ethanol. Answer is B, as I said. So this one is also out. Answer B. Okay, number 35. Methanol is a naturally occurring alcohol. Menthol, not methanol. It's menthol. Okay, when menthol is heated with concentrated sulfuric acid, it reacts. Okay, alcohol plus acid. This is esterification, right? No, it's not a carboxylic acid, so it can't be. Concentrated sulfuric acid is a dehydrating agent. Okay, since it's a dehydrating agent, we are going to remove water. The products formed include compound T. What products? Include compound T, so it's not the only one. What is the structure of compound T? Oh, so I need to remove this OH together with maybe a hydrogen that's here or a hydrogen that's there. Right, so then when I do that, I get two products, depending on which one I have removed. So one is major, one is minor product. And then also I get water, the water that has been removed, isn't it? So if I remove the hydrogen above, then I get something like this. I get a double bond here, and then I get this. So this is the compound you get. If you remove the hydrogen below, you get this guy, a double bond to this side, and then that. So we're looking for these compounds. Is this one there? No, there's no one with a side bond here. It's not there. Okay, so it's not there. Is this one there? Yes, it's there. It's this one, only that it's flipped. they've kind of rotated it like this. It's the same thing. It's just been rotated. It's still the same thing. Can you see? It's rotated. It's the same thing. If you don't believe, let's check the other ones. Let's check the other ones. How can you, when you remove this OH here, how can you remove with the hydrogen here to form a double bond here? This doesn't make sense. Out. And here they just remove the hydrogen. No, concentrated sulfuric acid is a dehydrating agent. It removes water, not hydrogen only. So wrong. This one, they remove the bond here, up here, and the OH is down here. Wrong. Yes, so answer is D. We're right. Okay, answer is D there. Okay. Okay, let's continue with the way of marking these answers. We marked this one. We said answer here is D. 36. Which compound will produce a yellow-orange precipitate when added to 2.4 dinitrophenohydrazine? 2.4 DNPH is used to test for carbonyl compounds, not alkenes. We use bromine water for this one. Not esters. This one we can hydrolyze with acid or alkaline. Yeah, acid or alkaline hydrolysis. This is a carboxylic acid. You don't use dinitrophenohydrazine to test for carboxylic acids. Out. Answer is D. Yes, this one is a ketone. Correct. Okay, ethanol undergoes an addition reaction with HCN in the presence of cyanide. Oh, we already discussed this one. Let's say this one was potassium cyanide. Let's say. Okay, let's say it was potassium cyanide. Just say. Which row identifies the type of reaction and the name of the product formed? We know this reaction. We have ethanol undergoes this. So if you have ethanol, right? This is, if you go to a chapter in the book on carbonyl compounds, you remember this. This is ethanol, right? Ethanol, this is ethanol. So this carbon is partially positive, right? So we can attack that carbon. And then we can push this one, and then this one becomes negative, you see? So we can do that. Or attack from that side as well, whatever happens. So we have hydrogen cyanide. So what's going to happen is that you are going to have a situation like this. Why did I erase that? I want to show, let me show you what happens here. So you have this one, and then you have CH3 here. And since it's an aldehyde, this one is like that. So when you add hydrogen cyanide, the cyanide ions, the other ones are catalysts, right? So you are going to have CH3, and then you have C, then the hydrogen joins, the hydrogen from hydrogen cyanide joins with this O, then you have OH. This hydrogen is still there. The cyanide from the hydrogen cyanide comes and attaches here. Then you have hydroxynitrile. Remember I told you when you have two functional groups in the same compound, you don't, OH is no longer alcohol, it's hydrox. So this is hydroxynitrile. And if it was carbon, if it was a carboxylic acid, it would have been carboxy something. So something like that. Like notice in amino acids, we don't say amine, we say amino, because it changes because of the presence of another functional group. Okay, so we form an hydroxynitrile. So makes sense because they've given us all the products they gave us a hydroxynitrile. The type of reaction is an addition reaction. We added hydrogen cyanide, so it's an addition reaction. But what type of addition? This one is a nucleophilic addition reaction because we are adding cyanide nucleophile. That's the one that attacks the positive carbon. So answer is between C and D. But now let's name it. They said you're starting with ethanol. If you start with ethanol, now you end up with how many carbons? Look, 1, 2, 3. So it becomes propane nitrile, 2-hydroxypropane nitrile. Because at position 2 we have hydrox. But how many carbons? 3. So 2-hydroxypropane nitrile. So which one is 2-hydroxypropane nitrile? Answer C. 2-hydroxypropane nitrile, not ethane nitrile, because we now have 3 carbons, isn't it? 38. The structure of compound X is shown. There is X, it's a cyclic ester. This is a cyclic ester. This is an ester group. O and C double bond O, that's an ester group, but cyclic. This is a cyclic ester. And then they say what is produced when X is heated with, okay, so this is alkaline hydrolysis of an ester. Alkaline hydrolysis. We are breaking down this guy. Sodium will go and join to this oxygen. No, in fact, no. I'm wrong to say that. We break here. This is the ester bond. We break it. And then there, this side, we are going to add O, Na, so this one. And then on the other side, we add hydrogen, and then this becomes OH. So we need OH next to a methyl, so branch, OH and methyl, OH and methyl. This one is not OH and methyl branch, so wrong. Not OH and methyl branch, wrong. So my answer is between C and D. Now the other side we said is we have ONA because of the sodium hydroxide, the sodium. So obviously answer C. This one doesn't have ONA, out. Okay, 39, almost there. The infrared spectrum of compound L is shown. This is compound L. Take this out. This is fingerprint region. We take it out. Fingerprint is out. Right. And This one, the bond that absorbs just below 3,000, you know it's the alkane bond, this one. Okay, so this one is the C to H bond. The bond just above so around 3,500. 3,500, 3,500. This one, amide. No, there is no amide. We don't have amide. We don't have amide. This one, 2,500 to 3,000. No, this one is above that. So 2,200 to 3,600. Yes, that's a hydroxy. So this one is a hydroxy group. Hydroxyl, like this, it's hydroxyl. So which one? A, he has got a hydroxyl. He has got a ketone. And this one, we didn't see a ketone, so out. B had hydroxy, aldehyde. This is an aldehyde, guys. Please notice this, out, because we didn't see an aldehyde absorption peak. Sorry, I'm dropping my head again, looking close to my laptop. But anyways, OH. This seems to be the answer. OH, carboxylic acid, we didn't see it. Answer is C. Did we not see carboxylic acid? Yeah, we didn't see anything between 2,500 to 3,000. We didn't see it. Answer is C. Number 40. And last question, guys. Okay, I've done it. You see, if you want me to do more of this, I will see if I get time, then I can just get a paper and then I can work through it. Hopefully it will help you. In the mass spectrum of compound J, the ratio of the height of the, of the M+1 peak to the height of the M+ peak. This is the molecular ion peak. This is the molecular ion +1 peak. So this is the one next door, the carbon-13 one, if you will. That's the carbon-13 one. Compound J forms a carboxylic acid when heated with this. So compound J will form a carboxylic acid when heated. Carboxylic acid, you can form, so remember, this is an oxidizing agent. Potassium dichromate 6 is an oxidizing agent. Potassium permanganate 7 is an oxidizing agent. So that means compound J can be oxidized to a carboxylic acid. You cannot oxidize a ketone. B is out. This one, propane nitrile, you cannot oxidize it like that, carboxylic acid. Okay, let's wait. We'll pack that. Don't think so. Not that one. Because you cannot oxidize this one to carboxylic acid. I wouldn't think that. So I'll put this one out. Let's look at A and C. A and C now, aldehyde. A is an aldehyde. Can you oxidize an aldehyde to a carboxylic acid? Yes. Yes, you can oxidize an aldehyde to a carboxylic acid. Because remember, you oxidize a primary alcohol to an aldehyde, then an aldehyde to a carboxylic acid. So A, possible. C is a primary alcohol because the OL is at position 1. So also can be oxidized. So that chemical statement here, this chemical observation is not going to help us. So maybe we need that information above. Boy, yeah, I see. So we just need to distinguish the number of carbons here. So I'll say, if you remember what we said in terms of NMR, we said number of carbons is equal to 100 divided by 1,1 multiplied by the mass of the molecular ion +1 peak divided by the M+ peak. So this gives me 100 times M+1 is what? M+1 is the first one, isn't it? It's 4, isn't it? Divided by 1,1 times 91 equal to, I hope I didn't mess that formula there, but let's calculate and see if we do agree with what we have here. We have what? 100 times 4. That's 400. Why am I doing that? Divided by 1,1 times 91. Right, good. It gives me 3.99999. My pen. It gives me 3.999 like that, 996, which is equal to 4 carbons. So which one between A and B is 4 carbons? 3 carbons, 4 carbons. Answer is A. We are done. We are done. That's it. Yeah, that's the whole paper. All right, so that's how we do it. If I made a mistake, please point it out. We'll talk about it. We can discuss it. Go through it. Again, I know these things can be boring, but again, it helps you. You have got to enjoy. I'm just trying to help. Bye, guys. And all the best with your studies.